Welcome. Today's lesson is Applications with Equations Day 2. In the Day 1 lesson, we looked at a variety of types of application problems, and specifically we looked at rates of return, we looked at mixture problems, we looked at uniform motion, and you know what, because uniform motion tends to be the most prevalent of these types that we're looking at, especially when you kind of think about standardized tests and stuff like that, figured we'd take a little more time and do a couple more uniform motion problems before heading into the fourth type, which you see at the bottom of your page, which happens to be job sharing. And actually, we've done a little job sharing before, but hopefully I can give you a different perspective on that as well. So we'll certainly follow the same format as the previous lesson, in that we're going to try to organize our information in a table and create an equation from that information in the table. So why don't we go ahead and get started here. I'm going to read the example 1 and ask you to do a couple things along the way. So example 1 states, two children, 224 meters apart, start walking toward each other at the same instant at rates of 1.5 meters per second and 2 meters per second respectively. When will they meet, and how far will each child have walked? All right, all well and good. Now it just so happens this particular problem actually allows you to create a table in two unique ways. So I have those written on my paper here, and I'm going to ask you to take a moment to see if you can come up with two entirely different ways to create this table. So here's what I'm thinking. And you don't have to do it physically, but I'm going to create a little barrier separating them. And because it's uniform motion, in fact, the nice thing about uniform motion problems, at least, is you don't have to worry about the titles of these columns, naming these columns. You just know it's going to be distance, rate, and time. So we've got that, and then it looks like there are two children here, so I'm going to do a 1 and a 2, and that's all well and good. Now, again, in a normal problem, you would just fill this out, come up with the equation, and kind of move on. That's great. But what I'm going to ask you to do just for this particular problem is come up with a secondary way to create that table. See if you can come up with two. So if you're ready, take a moment and then come on back and let's see how you did. All right. So here's what I was thinking of when I looked at this. I first of all kind of scanned the problem, and the one thing that jumped out at me right away, I'm always looking to fill in one of the columns numerically because to me that's the easiest. So it's like, all right, that's easy enough. We have the rates, so I might as well throw them in. That's really nice. And then what kind of jumped out at me as I initially read this problem is at the very beginning of it, they're 224 meters apart, and they're starting to walk together. Okay, that's great. So what that meant to me was one of the children is going to walk a certain number of meters, and because I don't know that value, I just called it x. And rather than introducing an entirely different variable for the distance of the second child, I figured out that, well, if one of them was x and they're 224 meters apart to begin with, then this child would have walked 224 minus x. And now I've got a situation where numerical values are in one column, variable is in another column. I can combine those in the third column. So again, uniform motion is nice because if I'm looking for time, which I am in this particular table, time very simply is distance divided by rate. So the time that child 1 had walked would be x over 1.5, and the time that child 2 had walked would be the 224 minus x over 2. Now, why don't we go ahead and just solve the equation, and we'll get an x equals here, and then we'll move on to the second piece. So once we have our third column, now we have to actually set up an equation from that column. And so the question really is, what do we know about the times of the children? And in this particular case, they start walking toward each other at the same instant, and obviously they're going to go until they meet. So from my perspective, it seems like they've walked the same amount of time. And so the time of child 1 is equal to the time of child 2. And so we set up our equation right there. And this hopefully won't scare us too much. We're just going to cross multiply. 2 times x is the 2x. And just grabbing a calculator if you need it. 1.5 times the 224 minus x. 1.5 times the 224 will give us 336. And then minus 1.5x. Add that 1.5x over, everybody, and we get 3.5x equals 336. And lastly, divide by the 3.5, and I get a value of 96. Now I'm going to hold off on that for the moment and just say, okay, great, x equals 96. Perfect. Now, before I answer parts A and B of the problem, I'm curious if you were able to come up with a secondary way to create your table and hence create an equation. So here's what I came up with. And again, I start out nice and simple. I know the numerical rates, so I throw those into the mix. And then the other thing that kind of jumped out at me is, well, they started walking toward each other at the same instant. Well, that means, again, that they've walked for the same amount of time. So if I have that as my variable, the time that child 1 has walked, then that would have to be the same variable because they're the same. Awesome. Now I've got numerical values in one, I've got variables in the other, and I'm going to use those 2 columns to create the third. Well, distance, as we all know, of course, is equal to rate times time. And so the distance of child 1 would be 1.5x. The distance of child 2 would be 2x. And I have that column filled in. Now that's great. Now I just need to be a little careful here. How can I create an equation coming up with this column that I created? Well, they're not the same. Remember, the distances are not the same. We want to go back to the information in the problem, and I look at they are 224 meters apart. So the distance that child 1 traveled plus the distance that child 2 had traveled is equal to 224. So again, we just have to be a little careful. Maybe one of these tables and equations kind of works better for you than the other, but certainly both should be legitimate here. Let's go ahead and solve this. I get 3.5x equals 224, and divide by the 3.5, and when I do that, I get 64. Now, before I go into panic mode, I guess I'll pose the question to you, why did I get 2 different numbers for x? If my tables are the same, why did I get 96 over here and 64 over here? Well, I hope you saw that in the table, the variable represented 2 different things, right? In this one, it represented a distance, and in this one, of course, it represented a time. So it doesn't matter which one you utilize. I'm going to go for it in this one just for kicks, but in this case, that's 96, which means that the distance that the other child had traveled would be 224 minus 96. So, and you know what, I don't like putting that x equals 96 there, but that's all right. Let's just answer the question itself. Cool, so how far did they travel? One was 96 meters. And then the other one would be 224 minus 96. And if you do 224 minus 96, you get 128. So we get 128 meters for that one. All right, perfect. Now if I wanted to know the times, well, I could still use this table, right? So think about it. I know the time is x over 1.5. Well, we just found x. So if I do 96 over 1.5, I would get my time. Or I could do it here, 224 minus 96 and over 2, and that would also give me my time. So if you have a moment and you have your calculator handy, maybe this one right here, do 96 over 1.5, and you should get 64, which would be 64 seconds. Oh, and hey, by the way, did you notice that's what this is equal to? And because that represents time in this table, we know that that's the case right here. So again, just knowing what your variable represents is extraordinarily important with these problems, because then you can answer the defining pieces of the problem itself. Okay, great. Let's move on to the next one. So example 2 states a tugboat can travel up the Mississippi 66 miles in the same time it can travel 90 miles downstream. If the current is 4 miles per hour, find the boat's speed. And this is a very common type of uniform motion problem. To me, it is an extraordinarily oversimplified version of reality, but we're going to go with it anyway, all right? So I'm just going to show you how these particular problems work out. Now again, it is a uniform motion deal, so if you would, distance, rate, time, and tugboats traveling up and then down. And let's see what we can fill in our table. Feel free to pause the video and do it yourself and see if that works for you. But I'm going to go ahead and see what I have. So it can travel upstream, so against the current. Obviously it's going to travel fewer miles than going with the current. So we've got 66 up and 90 down. That was easy to plug in. Now here's where we're going to use our current of 4 miles per hour. So what we have is the boat's speed. We would call it the still water speed. So that would be without the aid or going against the current. And that's going to be our x. So the x will represent the still water speed. And if we're going up, basically we're being hindered by the current by the speed as 4 miles per hour. So we would write the current going up as the still water speed minus the current speed. Whereas if we're going downstream, we're getting the benefit of the current's rate, and so we would add that on to the still water speed. So that's where this comes into play, this current of 4 miles per hour, either going against the current or with the current. Okay, now like we kind of did in the last one, I've got numbers in one, variables in the other. Let's combine them to get the third. Distance divided by rate is equal to time. So I know the time here is 66 over x minus 4. And I know the time here is 90 over x plus 4. All right, now what do I know about the times? And this is where we want to go back to the problem itself and read the situation. And for me, it really just comes down to those two words right there. So same time going up as going down. So time upstream equal to the time downstream. And I don't want to go through that too quickly. I do want to make sure that you are very aware of coming up with the equation from the remaining information in the problem. What do you know about the times? Well, in this case, we know that they are equivalent to one another. So I can set one equal to the other. Okay, well, if you have your calculator, you can go ahead and cross multiply here. I'm going to go ahead and do it without. So distribute the 66 in, and looks like I get 66x, and how about a 264? And then cross multiply here. Looks like I'll get a 90x, and how about minus 360? And solve this however you'd like. Of course, I'm going to bring that 66x on over to the other side. So 90x minus 66x, that would give us 24x. And in the same breath, I'm going to add 360. And so that would give us 624 on this side. And if I divide, 624 divided by 24, I should get 26. That's great. And before I pat myself on the back and for a job well done, do you want to make sure I've answered the problem here? So if I'm looking for the boat's speed, and I interpret that as how fast is the boat traveling going up river, and then how fast is it going down river. So this is the still water speed, remember that. So this would be 26 miles per hour as a still water speed. Going up, I'll take away the 4. Going down, I'll add the 4. And so I'm kind of thinking of it as 22 miles per hour up, and then 26 plus 4, that would be 30 miles per hour going on down. All right, very nice. So just a couple of uniform motion problems. As you can see, there's some benefits to working in uniform motion, and to me the primary one is you can take some of the thinking out of creating these column headings. It's just distance, rate, and time. Perfect. Let's move on. So last one here is the fourth type. And again, just wanted to rehash that we've done rates of return problems, we've done mixture problems, we've done uniform motion problems. We've already looked a little bit at job sharing, but I'm going to show you a different way to do that using a table here with a more complicated variation of job sharing. All right, example 3. Bruce works for 15 minutes fixing his hot tub. Then Angela helps him, and together they finish in 20 minutes more. All right. If Bruce could have done the job alone in 1 hour, how long would Angela take alone? There's a lot going on there. So as I wrote on your sheet, and I'll go ahead and read this momentarily, we're going to try to make a table. So it says, let's try making a table for job sharing. I didn't do that last time around, but I think it's going to work nicely here. And we can do that in a very similar format to the uniform motion problem. So this is going to fit nicely. So do you remember for uniform motion, right away we just made our columns as distance, rate, and time. Well, for job sharing, what you can do is actually as the job, the rate, and the time. Now you could do J, R, and T if you really want to, but as I'm presenting this, I just want to make sure we're clear what each represents. So job, rate, and time. And job is going to be equivalent to the idea of distance, if you can kind of think about that. All right? So we've got the job, rate, and time. Now we've got a couple things going on there. With job sharing, remember, one person is working individually. That's Bruce. Second person working individually, that's Angela. And then job sharing, so at some point in time they work together, and so we've got Bruce, Angela, and together as our 3 rows going across here and here and here. All right, well, let's see what we know in this particular case. Now again, this is a little bit of a harder variation, but you can absolutely use this table for the easier variations of these, and in fact it works really cleanly. All right, so Bruce works for 15 minutes. That's great. It doesn't tell us much, just the time that he does part of the job. Then Angela helps him, and together they finish in 20 minutes more. Okay, so they were working together, right? And the time that they work together, that is definitive there. That is 20. All right, so I'm going to put that in. And then it says if Bruce could have done the job alone in 1 hour. All right, that's actually a very important piece because we want to know the time for him. And in this case, Bruce by himself, the whole job would be 60 minutes. How long would Angela take to do the whole job? So that's our X. So I'm hoping you see that piece right there. Bruce would take 60, Angela would take X minutes. Together they took 20 minutes. Now, here's what I'm thinking. Think of job almost like as a distance, but it's like how much of the job are we talking about here? Well, for Bruce, it says could have done the whole job, so one job in 60 minutes. So I'm going to put a 1 for Bruce there. Now, if you look, it is saying how long would Angela take to do the whole job by herself. So for her, it's 1 full job. Now, here's where we're going to be a little careful. They didn't do the whole job together in 20 minutes. They only did a fraction of the job together in 20 minutes. So as you're looking at this problem and you're seeing me fill in the table, you're probably or potentially asking yourself, well, what about this information? And here's where it comes into play. So Bruce worked for 15 minutes fixing his hot tub, right? What fraction of the job was Bruce able to do in that time? Well, if it takes him 60 minutes to do the whole job, and he worked for 15 minutes, I'm not going to write this down, but you can if you want to. Somewhere, Bruce did a quarter of the job by himself, right? So he worked for 15 minutes. He could have done it in 60. So 15/60ths of the job means he's done a quarter of the job, which means when Angela then joins and they work together, that's not for the whole job because some of it was already done. It's for 3/4 of the job. So this is what makes the variation a little more complicated. Okay, now watch how this plays out. Remember, it's equivalent to uniform motion. Think of the job as equivalent to distance. Well, how do I get the rate? Distance divided by time. So if Bruce was able to do one job in 60 minutes, he's able to do a 60th of the job every minute. That's how fast he works. Distance divided by time. So this would be the rate for Angela. Distance divided by time. And again, when we talk distance here, it's the amount of the job done. So this one's a little different. Got a little compound fraction going there. But that would be 3/4 over 20. Now this should look familiar. As we talked about job sharing before, the rate of one person plus the rate of the other is equal to the rate of them working together. Think of it as how much Bruce can do in a minute plus how much Angela can do in a minute is equal to how much they can do together in a minute. This plus this equals that. And so that is going to be our equation here. I'm going to see if I have enough room for this. But 1/60th plus 1 over x equals 3/4 over 20. Now, a couple things you can do here. If you don't like this 3/4 over 20, what you can potentially do is just multiply the top and bottom by 4 right away to get rid of this little denominator of 4. And you can get, it looks like that would be 3/80ths right here. That would work, absolutely. What I think I'm going to do is, I think I'm going to do it this way. I'm going to just solve it as it is. No reason not to, I guess. So you can clean up this little compound fraction here if you want, but at the end of the day, it's not going to make a difference. But I do have a situation where I've got two fractions added together equals 1/3 on the other side. And I'm going to come up with an LCD. And so we've done this certainly before. And it looks like the least common denominator of 60 and x and 20, from my vantage point, looks to be 60x. So I hope that does work for you. So again, what's the least common multiple of 60 and 20? It's actually 60. And then don't forget, obviously, if x is part of a denominator, it needs to be part of our LCD there. Okay, well, I'm going to just multiply everything by 60x and see what happens. So the 60s would just directly cancel right here, so I get x times 1. That's x. That's nice. And let's see, in this particular case, when I distribute that into here, it looks like the x's will cancel. So I just get 60, also nice. Now here I'm going to be a little careful when I distribute this 60x into this fraction, and careful with me, it looks like the 60 over 20 would reduce to 3 over 1, right? And so I've got 3 times the 3/4 there. And sorry, hang on just one. Okay, sorry about that. As I was saying, if we distribute the 60x into this fraction right here, well, I get my 60 divided by 20, and that would be 3, so I have a factor of 3, and then 3 times 3/4, that would be 9/4, just from what I'm seeing, and we certainly can't forget that x. So as a result, I'm getting 9/4 x, or 9/4 would be 2.25 there. And again, feel free to use a calculator to just distribute this in. And as I said earlier, if you don't like this compound fraction, you can rectify that first, then come up with a different LCD on this. But this should hopefully work out, because now when I solve this, think of this as a 1x. I'm going to subtract that on over. So I get 60 equals 1.25x. And I'm going to go ahead and divide by 1.25. And when I do that, 60 divided by 1.25, is equal to 48. And so I just want to make sure that my solution to the variable answers the question, how long would Angela take alone? That's exactly what it represents right here. And so our final answer would be 48 minutes. So I really like this for all job sharing. If there's no weird variation for job sharing, then you can just do one job, one job, one job, and it works out really nicely. But if you kind of equate it to a uniform motion problem, I think it just makes the setup quite a bit easier. And just remember the rate of one plus the rate of the other is equal to the rate together. All right. So now we've done 4 different variations of applications with equations. If you have any questions or concerns, be happy to walk you through as many as possible there. So thanks, everybody.